This class is the continuation of last one, and in the last class, you are talking about the Bode plot of frequency response, and particularly you are discussing this standard second order equation. This second order equation is very popular and most frequently mentioned in the control theory and the network theory. Maybe this is very important. They think it is important, and actually this is important. Okay. Then why you are studying this? You are studying something else, but converter, closed loop control, and everything. And we suddenly jumped in this familiar topic. The reason for that is eventually you want to have the knowledge about the dynamics and the control of PWM converters. So the method I have taken is frequency response based method. So for that, we need to know the frequency response, and the frequency response is defined for the linear time invariant systems only, but we want to adapt that to the nonlinear time varying PWM converters. So we need something, okay? So first we review this classical theory. I think most of you are already familiar with this. Then based on that, we figure out how to modify our PWM converter to adapt this kind of story. In other words, you want to apply the older existing knowledge about the linear time invariant systems, like this one, frequency response of linear time invariant system. And actually, we need some modeling process, but we skip modeling process now, and we will go there later. Modeling, okay, is a huge topic, okay, that we will cover later. So what we are trying to do is, first we understand this, and we try to understand the implication and the limitation of this Bode plot frequency analysis applied to the PWM converters. But there are good relationship between the response of linear time invariant system and the response of PWM converters. We understand that, and later we study the modeling of PWM converter. Then the story will go much smoother and much faster. Okay? Previously, after finishing the closed loop control of PWM converter, I explained all the topologies of PWM converters, transformer isolated version, non-isolated version. After that, I delivered the story about the modeling. Okay, so that is the classical approach. But somehow I like to change the order of this teaching. Okay, maybe this is a top-bottom approach or bottom-up approach. It's a different approach compared to my previous lecture. Okay, so now we study this one, and we went through this. Okay. And this is the double pole at this frequency, and it has peaking here. And this is double pole frequency, and starting from frequency, the slope of this magnetic curve is minus 40 dB per decade, and this phase is 0 in this area, and the final phase of this is minus 180, and there is abrupt change in the phase. And actually at this double pole frequency, this is the exact value. This is the only one exact value. Everything else is, you need to calculate this. This is available directly from this analysis. Other than that, you need some simulation or very, very tedious calculation. Okay? So, but this peak value is 20 log QP, and QP is the damping ratio. I'm sorry, quality factor. Damping ratio is a term of control engineering. In power electronics, we are using the quality factor. And this frequency is omega naught, which is given by 1 over square root to LC. Okay, LC. This is the exact value at this exact frequency, but actually this is not the peak value. Peak value really occurs in this manner. So let me draw that here. So I magnify this part here, and it looks like this actually. Oh, let me. Something like this. I'm sorry, something like this. And the peak value and this frequency. This peak value is actually larger than this one. Okay, this is not the maximum. This is slightly the left side of the maximum, and this real peak value is, of course, at this frequency is slightly lower than this frequency, and the deviation of this peak value and this peaking frequency is related with the quality factor of this circuit, and the exact magnitude of this one is 20 log QP, and we have something here, 1 minus 1 divided by 4Q squared, okay? And this omega naught is here, but this frequency, actually this frequency, which attains the peak value of this magnitude, that frequency, maybe we call it omega R. Omega R is given by, this is omega naught, double pole frequency, and we have factor like this, 1 minus 2Q squared in the denominator and 1 in the numerator, okay? So this is the exact one. So there are some observation. If Q is very large, this can be considered as 1. If Q is very large, this can be considered as 1, okay? For the large Qs, then they are the same, okay? Peak value is 20 log QP, and this frequency, peak frequency, is the same as double pole frequency of this filter, okay? But Q becomes smaller, less than infinity, then it goes up because of this term in the denominator. It becomes less than 1, and it becomes less than 1. Then this frequency is shifting like this, okay? So if you take close look at this, if you simulate this, and actually they don't match, okay, because there is a small shift. But that is not important, but this fact is there. So if you go to the textbook of the control theory or network theory or electronics, they are using this, okay? But after this moment, we forget about this. You assume Q is relatively large, means some number between 2 and 4, okay? It is a good number. Less than 1.5 is, then this double pole will be split into 2 dual poles, and it's some other story, okay? So this is one thing, right? I want to emphasize. And another one is there is a relationship between this Q is quality factor is related with this one, 1 divided by 2 zeta. Zeta is damping ratio, okay? This is damping ratio, and this is quality factor, and this relationship is written in this manner. Is the same equation. Zeta is 1 divided by 2Q Q, okay, same equation. This is used in electronics or power electronics. This definition used in control people, right? And one thing I'd like to mention is this Q goes to infinity. This quality factor is infinity. So it has the best quality as an energy storage element, okay? But if this thing is infinity, then this zeta becomes 0, means there's no damping, right? Take a look at that door lock, okay? If the door lock has 0 damping ratio, if you touch this, it will move forever, okay? And this Q and this zeta is related with energy stored compared to the energy dissipated. This means, this is infinity means there is no energy dissipation. So, and this means the same thing. No energy dissipation. That means what? There is an exchange, lossless exchange of energy between L and C without any loss. All right? That means lossless exchange between L and C. Okay? It's called resonance. This phenomenon is called resonance, but we want to avoid this for this case. Very large Q is hurting us. Okay? For the resonance converter, which use this lossless energy resonance, Q, high Q means the better operation as a converter. Resonance converter, high Q is desired one, and for the PWM converter, some number between 2 and 4 is desired. Okay, then make difference. And this lossless energy exchange appears as periodic oscillation, sustained oscillation with constant magnitude. Magnitude not changing because energy dissipation is 0, and this frequency corresponds to double pole frequency of this. Okay, that is related with resonance, and the resonance converter is making use of this feature. But now we are not interested in that because we are talking about the PWM converter. PWM converters, if you design this type of filter, double pole filter, convert probably 4 is the desirable value. Okay, high Q means the converter becomes very oscillatory, and resonance converter, you are making the use of oscillation. Is entirely different story. Okay, so I want to deliver these two things on this page, and frequency response and step input response. You have this standard second order equation, coordinate function, and usually you are interested in this step input response means this RT is jumped up to 1 and it stays 1 forever. Okay, that is the unit step input response is important. For this, why is that? There are many different kind of input, but we are paying particular attention on this because this step input response can be some metrics to evaluate, to judge the quality of this. It provides good step input response. It provides good dynamic performance for any type of step input response. Okay, so this is the one people use as to evaluate performance in general. Okay, then this good step input response means good transient response for any type of input disturbance. Because of that, that is important. Okay, for the PWM converter, you are not changing input voltage open. You are changing load current very open. Okay, for this case, step load response is very important. So later on, we will be discussing this in detail. Step load response is coming from the output side of this system. Right? This one is important for the PWM converter because the load will be changing all the time. So many times input is fixed or input is gradually changing or input has very small ripple component. So this step input response has less significance compared to this one for the PWM converters. Still, you are interested in this one. Okay, so the standard way of this is transfer function, and this is what S domain is expression of this step unit function. This is 0 and this is 1, and Laplace transformation of this waveform is this one. So this is the input, and this is the transfer function, and the input times transfer function is output in S domain, and you take the inverse Laplace transformation, then you obtain this result. This is the step input response of this standard second order system, and this is covered for the older control books. Okay? So deriving this is not important. You need some tricks to derive this equation, but it is full covered in many books. So I'm using the book from the Bob Erickson, Fundamentals of Power Electronics, and he derived this for me. So he is a very good guy for me. So I'm using his result, and this plot is taken the control book, Bishop control book. It's not very good book though, but it's okay. So this is Bode plot of this equation, and this is the shape of general shape of step input response. Okay, you are familiar with this. Okay, but understanding this is important. The output is composed of three components. First one is constant. Here, input is 1, then output should be the 1. Okay, because we have 1 here, right? So this is the transient response. This term will be disappear in time. Okay, eventually they die out. It dies out. But this one is consists of 2 terms. This is a decaying exponential terms. This is a decaying. Dying out term, and this is what? Oscillatory term, oscillation term. Okay, this is oscillation. Maybe it has some fixed frequency and fixed phase. It is sustained oscillation, but it has damping term here. So output is this one. So it goes like this, and eventually this guy dies out, and the remaining value is what? DC. This is the steady state. I told you the steady state means all the AC components, they die out, and this DC value is remaining. So eventually we will get steady state here, and the output becomes 1, same as the input. Okay? So you don't have to remember this, and you don't have to practice to derive this, just know this fact. Okay? There are 3 terms, and this is the steady state term, and it is multiplication of this constant frequency, constant magnitude sinusoidal oscillation multiplied by decaying terms, so it dies out like that. Okay, so this is one thing I'd like to mention it, and this one, so this is asymptote, and this asymptote, but during this region, it deviates from the asymptote. Okay, this much. So for this particular case, this is error. So maybe we use straight line approximation, then this might be error. Okay? So behavior of circuit around this double frequency highly depends on the value of the QP. So you need some additional information about that. So this is QP of 5 and 1, 2, 4, 6, 8, 10, like that. Then the QP becomes larger. So larger peaking implies this is larger Q. Then that means larger peaking. Okay, so 20 log Q peaking. This is the peaking, right? And if Q becomes larger, the phase change becomes steeper and steeper. Okay, if you increase Q, it becomes bulging up, and this becomes steeper. So this is the direction of larger Q. Right. So I simulate this with PSpice according to this range. This is 1/3 of double frequency. This is three times of double frequency. So there is some variation in this manner during that frequency. This is very different from the single pole or a single zero case, but we already know this, right? We already know this is the maximum of this, and we already know the phase change like that, and this merges, this is what? This minus 90 degree, okay? So at this frequency, this phase is exact, and at this frequency, this value is very good approximation. For the high Q situation, error becomes negligible, right? And how about this? So you are increasing Q in this direction, you are increasing Q in this direction, then this corresponds to the step impulse response of large Q, smaller Q, further smaller Q, so on, right? If Q is increased, okay, take a look at this direction, this peaking is increasing, but this dying rate remains the same, okay? That depends on something else, okay? The decaying rate depends on not only this QP with another term. We don't want to go that details because that details are covered more than necessary in those books, okay? And take a look at this. There is a slight peaking, overshoot, and with this, the peaking is gone, and with this, the peaking is gone, okay? So they behaves like first order system. So at this time, this is a sinusoidal waveforms, and this is exponential waveforms. Sum of two exponential waveforms. So each of them looks like first order system. First order system, okay? And this is the equation. Equation is too long, so it goes like this. And this is called the quality factor, and this is called the pole frequency, okay? This is all about the frequency response for the linear time invariant system. We covered several things, okay? All right. So important thing is all of this analysis is exact evaluation of this transfer function, okay? We used this, and we used the exact equation of the magnitude and phase, okay? We did the same thing for the first order single pole and the single zero. We used the exact equation, this evaluation of this magnitude and the phase of the complex quantity is done. But this one is based on the exact analysis, but this is bad approach, okay? You want to use something simpler and something much useful and something more insightful. It provides all the information about the system behavior. That is called asymptotic behavior or asymptotic analysis or asymptotic plot. Okay, so that will be covered in the next section. So we take a short break here.